Today we are going to do section 3.3. So first, let's scan the books in. Let's see. This is okay. This page has already been scanned, so we'll just focus on the new part. I'll put it a little closer. All right. That should do it. Next, page 98 and 99. Let's see that. Okay, that should be it. A little closer on top. I'm not able to. Okay, there we go. And then a little closer on the bottom. All right. And finally, page 100 and 101. So we're past the page 100 mark. Okay, that's good. Let's see, a little closer. Maybe move this way. Yeah, that looks sort of okay. All right. And then let's zoom in on top a little bit. Okay. And then the bottom. All right, that should be it for today. So today we are going to do subsection 3, curvature and torsion. We already studied curvature to some degree in calculus 3, okay, before this, but we're going to develop it in more advanced way in this section. The curvature, of course, is about turning, like when you're driving and you're turning, and then that causes you to get off get away from the tangent. However, curvature, you're still on the same plane. Whereas torsion means you are turning, but now you're turning into the sky. Basically, an alien is abducting you, and your whole car is tearing off into the sky, or got dug into the ground. Either way, so that is torsion, and as a result, then. For a plane curve, the torsion is 0, of course, because you're on the ground. And this is a fact that you will prove in the homework. All right. So that's about all we have to mention from the past. So please read that paragraph yourself, the first paragraph, carefully, and then let's look at the definition of curvature, the new definition, which is defined very interestingly as 1 over r, r being the radius of the curvature, is defined as the limit as delta s goes to 0. Okay, delta s, we're defining it along the arc length, so delta s is the arc length change of delta theta divided by delta s, whereas delta theta is the angle between the old tangent at the delta S0 and the new tangent, where S0 is being added to a delta S. And that's where the delta S is going to 0. Of course, as delta S goes to 0, the angle between the two tangents will reduce, assuming your curve is reasonable. Does it even say that? I guess not. Doesn't matter. Well, if it's defined, of course. And so it is such that the limit exists, right? And so so that is the basic definition: is the angle between the two tangents divided by, say, if you have some angle here, okay? As it approaches, the angle goes to 0, but so does delta s, and the fraction exists in the limit. Then that would be defined as the curvature, which turns out to be the same curvature that you learned in calculus 3. But we're not going to think too much of what happened in calculus 3, but rather focus on this, okay? So that is our new definition. Now, knowing that that's the new definition, let's do an example of it, okay? We have some circle. This is just a circle, and which, of course, designed with a sine something and then cosine something. And then we are going to calculate the curvature at some point, S0, which is any point, okay? So then let's do the calculations based on just the definition alone. Now the tangent, of course, equals to alpha, okay, and which is alpha is defined as x prime of s. So let's calculate x prime of s, of which I get a bunch of stuff, okay, and then next. Then the tangent, when you moved a little bit, you moved from S0 to S0 plus delta S, then we'll plug the new value of S in, which is S0 plus delta S. And then we're going to calculate the delta theta by doing the cosine. Okay, take this dot this divided by its unit, magnitude, I'm sorry, which gives you a bunch, once you do the dot product of those two things, okay, and gives you this formula if you do it patiently. So please verify all this yourself, okay? Do this example yourself as well, but this is it's pretty straightforward, though, in other words, a bit tedious. But it can be done, and then you will come up with this formula, which looks familiar because it is the sine, please Google this formula, it's the cosine difference formula, which looks like that. So you apply the formula, and you get cosine delta theta to be something very clean and neat. Cosine delta theta happens to be delta S over A. A is some number that's related to the original formula. So then that means the delta theta is delta S over A, and by definition then 1 over R is equal to 1 over A. Okay, that is eventually what we end up having on the following page. And then if you remember from curvature in calculus 3, the R is the radius of your turn. That is, you're turning around the circle, okay? And the smaller the R is, the sharper your turn is going to be. So the curvature is bigger. And that's why curvature was originally defined, and still do, as 1 over R. But look at how interesting this definition is. If you define curvature as this fraction, that means curvature can be 0, okay? Even though in real life, no fraction can possibly be 0. But this way, this definition means the fraction can potentially be 0, because we define it as a fraction, and we really don't care past that point. Anyway, yeah. And anyway, so let's look at the next page, and that's how the example comes out. Now, in this example, of course, the curvature happens to be a constant, which is 1 over A, and that's because it's a circle. A circle, you turn by the same amount the whole time. If you turn your wheel a fixed amount, then you can go around the whole circle, and theoretically, depending on how exact your turning is. So let's look at theorem 4. Now I'm on page 98. Theorem 4 gives us exact calculation of the curvature, such that we don't have to mess with limits all the time. And the curvature's exact formula happens to be x double prime of S, which is convenient. Remember, x at this point is parameterized by S. We use the S parameterization. It's more difficult to parameterize a curve by S, but once you've done it, then the rest of the arguments gets a lot easier. Okay, for example, curvature is just the second derivative of the vector. And magnitude, of course. All right, so let's look at the proof of theorem 4. Now, to prove theorem 4 from the definition that we were given, we will go ahead and do basically the same thing we did in example A. First we write down the tangent at S0, which is alpha, right? And the tangent at the moved point S0 plus delta S is going to be alpha plus delta alpha. And we'll call it that way, okay? Which is, of course, x prime of S plus delta S by definition. And in the meantime, remembering that x prime of any value is 1, because S is the arc length parameterization, and that equals to 1 by a previous theorem. So then we calculate cosine delta theta. Again, it's the dot product of those two things. Those two vectors, alpha dot the change of alpha, which will be equal to 1 plus alpha dot delta alpha when you're done calculating, and which is equal to, when you manipulate this equation, then minus alpha dot delta alpha is equal to 1 minus cosine delta theta, which we'll use shortly. In the meantime, remember that alpha plus delta alpha is the new alpha, right? So it's still the tangent, unit tangent vector, and therefore its magnitude is 1. So to rewrite this situation, we write down, in other words, 1 equals to this vector, alpha plus delta alpha dot itself. So when you write it down, then you end up with this neat little equation where 1 is here, and you multiply out the dot product, okay? You get this pile of stuff, and then it also equals to 1, being that its magnitude is 1. So that's a trick where you eventually get this. So the middle part right here equal to 0, which I have written down here. I'll put it another way, is this thing is the negative of that thing, okay? And this thing is what, this equation is what we're going to use. We'll write that down here, which says, that is 2 times alpha delta alpha, okay, equal to delta alpha dot itself. But we're going to also divide it by delta s squared on both sides. And then we're going to apply equation 1, which says the alpha dot alpha is equal to 1 minus cosine delta theta. So we'll plug that in. So we end up with this particular equation. And we need to calculate delta s approaching 0. And that makes us engage a difficult point. And well, that's not obvious, right? So to make it obvious, however, we're going to use a trick. And the trick is this equation right here, where the limit of 2 times 1 minus cosine a over a squared, if you apply the L'Hopital's rule, you will come out to realize quickly that it equals to 1. All right, and we'll use this thing and plug it in. That is, this is our original equation that we're stuck on, right? And then what we're going to do is multiply this thing by 1. We already said this thing goes to 1, okay? So we'll apply this formula by having, this is this equation, okay? We have delta theta and delta s, and delta theta's squares cancels out here. So this is the same equation as that, with a trick stuffed in here. So we have a delta theta on top and delta theta on the bottom. So this, and then we let delta s go to 0. At that point, this thing just goes to 1, all right? And because as delta s goes to 0, so does delta theta. So this goes to 1, and that is delta theta over delta s, okay? Which is 1 over our squared, this part is. And then this thing, of course, is equal to delta alpha d alpha by ds squared. So so this is a neat trick that your book showed. Well, didn't exactly show, but it expects you to, work it out. And so then what we got out of that, all that stuff, is that then 1 over r, as defined this way, okay, which is delta theta delta s, is 1 over r squared, then equals to d alpha by ds. What is this? Is this and this is not a dot product. This is just multiplication, I think. Or is it a dot product? Let me think. No, I believe it's the dot product, okay? Anyway, so that's the dot product, which is fine. Dot product becomes a scalar when they dot themselves or dot anybody else. So then we have, therefore, that, so we got the equation for 1 over r, which, in the meantime, let's remember that alpha is x prime of s, therefore d alpha by ds is x double primed, and therefore 1 over r from here is equal to the double prime squared. So one of them is the magnitude of just one of them, right? So 1 over r is x double prime of s, and by that we have finished the proof, because that's what we were shooting for. So as you notice, it's a neat little proof with a bunch of minor vector manipulations and some neat trick from basic calculus of applying the L'Hopital's rule. And then and a couple other comments, okay? Because of what we have done, we also notice that beta is going to be, which is defined as, what's beta? X double prime divided by its magnitude. That's on page 95. And it's going to be, because of that, being that this thing is now 1 over r, you can write down beta as x double prime s times r. And alpha prime is equal to x double prime s, is then going to be equal to minus beta over r. Is there a minus here? Now let me check. No, it's not minus, it's just some equal sign. Okay, we have equals to, so because alpha prime is that part, okay, so beta times its denominator equal to, well, anyway, this works out, all right? That if beta, yeah, from this equation, beta divided by r will be equal to x double prime. Now, why is my camera not zooming in? Well, okay, there it is. Anyway, so there's a couple of details that might come in handy or not. It doesn't matter. The point is that it's the proof of theorem 4. And so let's, now that we proved it, let's use it for example A, which we were calculating the, what was it? The one, what are we doing here? Curvature, right. In example A, we calculated the curvature from the limit, which is somewhat convoluted because that's what happens when you calculate stuff from the limit. Now that we have a formula, of course, example A comes out much faster, right? Because the formula is just says something like A equals to, what was the curvature? Yeah, it's just x double prime s. The magnitude thereof. So all we have to do then is calculate its magnitude. And so that comes much faster. Yeah, it's especially faster if I can figure out where it is. Let me find it. Found it. So 1 over r, which is the curvature, is now just defined as a magnitude of x double primed with s, right? So then all we had to do is calculate x double primed, and then crank out its magnitude and plug something in, and then we got the 1 over a out right away in somewhat shorter and less work. So that please do that yourself as well. And in fact, prove this entire theorem, reprove it yourself, okay, without looking at the book, as you should do with everything other part of the book as well. So having said that, then let's move on to the next section. So next, let's go to the bottom of page 98, where we have the definition of torsion. And the torsion is given again as the limit of delta s go to 0, where some angle, delta phi over delta s. Now, delta phi is the difference of angle between the normal of the oscillating planes. Now, but what that means is that well, actually, it's the angle between the oscillating planes, which just means the angle between their normals, okay? Because the planes are defined by their two normal vectors at S0 and S0 plus delta S. Now, if you look at this formula carefully, which is delta phi over delta S in the limit, and then look at the formula previous page of the curvature, you notice that the two formulas are practically identical, except that the curvature has the absolute value on it, so that we don't care about its sign, whereas the torsion, the sign does matter slightly, okay? And we have a positive, or we allow it to be positive or negative based on whether this thing is a right-handed helix or not. The reason is because the torsion is twisting like a helix, sort of, that is twisting out of the plane. So the twisting happens, it can happen in the right-handed way or the left-handed way, okay? The twisting comes one way or the other. So we will assign the positive, if it twists the positive, well, if we twist the right-handed way, we'll call it positive, and the other way will be called negative. See, yeah, we mentioned the the right-handed or left-handed helix back when it was first introduced on page 72. All right, now let's just move on, okay? And just remember that torsion has a matter of being right-handed or left-handed. And so let's look at example B, where we have, now that we have the definition of the torsion, let's calculate it from the limit one time, okay, to get a feel for it. And then so we have a basic helix here, and we're supposed to, let's calculate the torsion the hard way. And so that is what I did, if I can, oh no, where did I put it? Let me find my example B first. So anyway, so being that torsion defined the difference between the normal of the oscillating planes, the normal of an oscillating plane is gamma, Okay, so that is what we're going to be calculating. Now, here's what I did. Please do this yourself as well. Okay, so here's example B. We have our helix, and we're going to calculate the two gammas and calculate their angles. Now, gamma is defined as x for s with parameter s is given as x prime cross x double prime divided by some magnitude. So I wrote it down right here. And then, which means to calculate gamma, we got to calculate both x prime and x double prime of the helix, which I have done right here. Okay. And so you take all these derivatives and stuff goes from sine to cosine and back to sine and that and negative sign, that sort of thing. And so eventually, then now after that, that's not all. You have to do the cross product, all right, which is what I did here. So there's the IJK business. Well, ignore this part for now, okay? That's the triple prime, which we'll need later, but I wrote it down here because, well, whatever. And anyway, but we'll look back at the triple prime, which just means you take yet another derivative. But for now, we only need the prime and double prime, so we calculate that thing here. And which and we also calculate the x double prime squared. That is its magnitude by taking the dot product with itself, and that gives this thing. Okay, and which in this case happen to collapse into a constant called 1/2. Okay, once you get done with the math, thanks to the sine and cosine, and being added up being 1. Squared, that is. And so gamma of s, then we calculate, well, anyway, gamma of s, what was gamma again? Is the cross product at, equals to this thing by the time we do this and that, okay? Its magnitude being 1/2, all right, or something. Well, whatever. Let me see, did I care about the magnitude here? I'm not sure, but anyway, gamma of s is something like this, okay? Hopefully I took care of the magnitude. And there's a 2 here, so maybe I did. Anyway, but we really only care about the direction here because we're going to be calculating the dot product, okay? Because we only care about the angle. We don't care how long gamma is. So that's not as critical here. Anyway, so gamma is this thing, which of course that's gamma S0 evaluates to this one. Gamma S0 plus delta S evaluates to this thing, and then we'll calculate cosine of the difference of angles. Now the cosine, well, this is exactly what we did in the previous theorem. Okay, we'll take the dot product and it equals to something, and then we are going to, it equals to that, and we're going to apply the same trick as the proof of the previous theorem, where you have this, you arrange everything to be delta phi over delta s. Yeah, delta phi over delta s, and times that 2 times 1 minus cosine delta phi over delta phi squared. So you have 2 so like in the previous page, okay? In order to calculate that limit, we pull this trick right here, okay? Where in order to, because this thing right here goes to 1, so we're pulling the exact same trick. In fact, the 2 proofs go identically because they're both about angles and the angle between 2 vectors. So then we pull the same trick, and then when this thing, and so then it end up being that. So please confirm all the details of the algebra here yourself. And well, by doing this homework, by imitating the proof of the previous theorem. So next, after all that, then what we get is that then as delta s go to 0, then the delta phi squared over delta s squared is going to be equal to 1 over t squared. The reason is now we're going to do another L'Hopital's rule, okay? Because if you calculate this limit stuff, then works out nicely to be applying L'Hopital's rule, I don't know, a couple of times, and it equal to 1/4, which means 1 over t is plus or minus 1/2. And then because the helix is right-handed, we'll choose the positive 1/2 as the answer. Yeah, well, anyway, the helix is, by the way, the helix is right-handed. It's mentioned earlier that I will repeat here, that the helix is right-handed if this value right, the coefficient before the k coefficient, this is the third one, is positive. Okay, at least that's what is said there, and that's all I care about. If you want to know the details, can check there. Yeah, why that would be the case. So, and that's good enough. I think that's what it said. So please check it yourself if you want to confirm for more. Anyway, so being that that k value, that is the third coefficient, is positive, we will choose +2 for the torsion of this thing. All right. And so please redo example B yourself, of course. So now let's look at theorem 5, where we have a nice clean formula for the torsion instead of being stuck with doing limits all the time. And the torsion formula happens to look like that, right, as shown in your book. And the proof is going to be quite interesting in a roundabout way, using several tricks. Now, the proof can also be, there's a more direct proof that will be shown in the homework, okay, number 14, 15, and 16, which you will be doing. But in the meantime, in fact, it's, problem 16 is yet another proof. So there are 3 proofs offered for theorem 5, but the first one we're going to look at, as presented in the book, is the most magical one, okay, and least tedious. So let's look at what the book has. The first sentence, it says, is that 1 over t squared equals to the gamma prime dot gamma prime. Now, where did that come from? The reason is because the definition of the torsion, okay, which is the limit of the difference of angles, right, of the osculating planes versus against the delta S, is identical to the in format as the definition of curvature, which is also the difference of angles, two angles of some two vectors against the delta S. As a result, the first part of the proof follows parallel. That is, as we have calculated before, that 1 over r squared is delta is d alpha by ds dot itself. Okay, that's in the same way that these two the vector here was alpha, right? The vector here is gamma, but otherwise there's no difference. All right, so that's why 1 over t squared is equal to gamma prime dot gamma prime, just like this. You just substitute everything in identically. Now, please do that yourself anyway, because I think it's a good idea. Okay, so like I did here, I just wrote down everything to just see from the ground up. Okay, which is also what the previous example did. So let's write. I wrote all this stuff out, well, which end up being exactly what I said before, and we calculate the same limit, use that same trick, okay, to calculate delta phi, delta s, and then end up with the exact same result. So please do that yourself, and we will move on as agreeing, starting from this point, that 1 over t squared, the torsion that is squared is gamma dot gamma. That is, the torsion is the magnitude of gamma. Then you take the square root of the thing. So now this is the point where your homework problem is going to start. Okay, we all end here, but the proof afterwards is what might become do more than one way to skin the cat. But up to this point is all proofs are the same. We got to get here. Is that 1 over t squared equals to gamma dot gamma. Okay, so then we still need to get the gamma prime, which means the magnitude is gamma prime. We need to figure out what gamma prime is in terms of the x and x primed and x triple primed and x primed, x double prime, triple prime divided by some magnitude squared and all that. Now to do that, so first, right now, we'll look at the book's trick. And the trick that the book pulled is that we're going to somehow prove this fact, that gamma dot itself, prime dot itself, somehow is equal to that thing, okay? And that's the, it's a bit like proving trig identities, okay? Things are the same, the sine is somehow equal to cosine doing something, and so on. So this is a similar situation where where one thing equals to the other. And you might think, but that's not really obvious. Where do you even come up with this? Well, you don't. Okay, somebody else, beat around the bush for a long time and figure this out. And now we are just gonna follow his path and see the magic come out. So to do that, let's move on. And let's get going. Where is this? Yep, this is it. So to do that is we're going to pull a whole bunch of small little tricks, okay, of vector algebra. I recommend that you do this yourself rather than listen to me explain it, because each are very small things that are much faster if you just crank it out by hand than listen to anybody explain it. But anyway, I'll explain it. I'll show you what I did here. So please do this yourself. Okay, so then beta cross gamma equals to, of course, beta is gamma cross alpha by definition. And then you get something like that, okay, with the triple cross product rule on page 64. And then gamma dot itself equal to 1 always. If we take the derivative of gamma dot itself, then you come up with something called gamma prime equal to 0. That is, of course, true with the other two normal vectors as well. And we've mentioned this before, but we're going to say it again. And also, alpha dot gamma is equal to 0, being that they're perpendicular. Then the derivative end up with something like this, and then a equal to 0, and then you have this relationship. So next, we have beta cross gamma primed. Then we substitute something. Alpha prime, where do we get that? I don't even know where I got that. Anyway, I got that somewhere. Okay, it makes sense. And then we have, and we're continuing. Actually, let me see. Oh, right, I got it. Now, because this part we showed that the something about this. Yeah, gamma cross dot gamma prime is 0, which means this part is 0, which means beta cross gamma prime is equal to that thing, okay, which I have written down here. And then next we're going to calculate alpha prime dot gamma equal to this pile of stuff, okay, which eventually equal to equal to this. All right, but by confirming, okay, alpha prime is the x double primed, gamma is that thing, and we write it out, that would be equal to, that, right? And then the beta dot, that equals to, that is beta, okay, cross this thing, which is going to be, let's see, what's this? And let me look at it again. Anyway, let's continue to explain this stuff. We have beta is, so this is beta. I multiply x double prime magnitude here and then divide it back out. So this thing right here is 1 over r, as we recently shown. Okay, this part is 1 over r, and that part is no, just this thing is 1 over r, sorry. And then this is beta dot gamma. Okay, this is the definition of gamma. So we got to this point. All right, and then next page. As a result of that, what's all this? Oh, all this is alpha prime dot gamma. So then, which is that thing, okay? So alpha prime dot gamma as that thing, which is beta cross gamma, is equal to all this. Let's substitute it somewhere. Equals to, if we substitute stuff in here, then beta cross gamma primed equal to all that stuff. Let me confirm that. Actually, it's right. Okay, so this thing, that's because this first part here is the alpha cross gamma thing from the previous page. Okay, and so that part is equal to that part. So this whole thing we will times gamma, which is beta cross gamma on my next page. All right, times gamma, and it happens to have beta dot gamma in it. Did it? Yeah, I did. So it happens to have beta dot gamma in there, and beta dot gamma equal to 0 because they're perpendicular, and therefore this whole thing, after all this work, and we only proved that beta cross gamma prime equal to 0, and as a result, if the dot itself is also 0, we then will, what is this? Yeah, we'll multiply the, what? Oh, sorry, cross itself. I mean, if the cross product dot itself, then it's still 0, right? And we'll apply the Lagrange identity and multiply it out and give us something like this. Now let me see where that come from. Well, anyway, so then from here, beta dot beta is 1. Okay, so we have gamma prime dot gamma prime left. The other thing is just square root of beta dot gamma prime. And so that whole thing equals 0. And then so what we get out of that is, well, in the meantime, you see what I mean? It's faster if you just do this yourself. Okay, it is as tedious for me to even explain it, but anyway, so beta dot gamma, of course, is 0 because beta and gamma are perpendicular. Let's take the derivative of that, and we get that pile of stuff over there, which means beta dot gamma is negative of, beta dot gamma prime here is equal to negative of beta prime dot gamma. And then that gives you, that substituting into this equation, which I rewrote here, means that gamma dot gamma is equal to, with the substitution, okay, equals to gamma dot beta prime squared. Okay, we just shifted the, yeah, anyway. So then, in the meantime, based on this definition of gamma, we have then, and then R equals to something to do with, yeah, 1 over magnitude of x double prime. So we can write gamma like this, and then beta then equals to, well, we already know this. Okay, I just wrote that down. Beta is x double prime times R. So, but we're going to take the derivative of beta. So beta prime is applying the, what is this, product rule? Yes, applying the product rule, we get this thing. And then, so then, what are we doing? We then get 1 over t squared, which was gamma prime dot gamma prime, which we have written, which have eventually, from equation 3 earlier, that we found out that gamma dot gamma prime equals the gamma dot beta prime squared, which I substituted in here. All right, so, and then after that, then we are going to, what is that? Yeah, then we are going to well, we're going to write down the definitions of this stuff, okay? So, which is equal to, actually, let me see what I wrote here. All right, I found it. So that's the definition, new definition of gamma, okay? That's beta prime. And we're going to substitute it in this equation right here, gamma dot beta prime. That is this thing dot this thing, beta prime right here. Okay, these two. So if you substitute those two equations in here, then you get this dot product, which is squared, but we'll take the square root so that we don't have to wear ourselves out. And so take the square root, there will be a plus or minus sign, which we'll write down, and equals to these things with dot product without, at least don't have to square. So then let's work out the dot product. What is it? So multiplying the dot product, the first term, okay, multiplying by, what is that? So multiplying by the dot product, where do we get? Let me read this a little more. Actually, there's not much going on. There's not much going on in this entire proof, except it's detailed and confusing looking. Anyway, so taking the dot product of two items added up, we'll dot each one, okay? And then dotting each one, if you look at it carefully, we have this is some rule of the cross and dot product is the determinant, right, on page 64. Anyway, we have, this will end up becoming x prime, x double prime, and x double prime. There's a repeated row here, which means this determinant is 0. So we are left with whatever's over here, which is, what is that? Yeah, there's a r squared happening, which I wrote it down as this way for some reason. Yeah, let's do that. So then, this is the denominator is the r squared, And then we end up with this side has x prime, x double prime, x triple prime, which then we suddenly got the formula that we were driving for, okay, with the plus or minus sign. And then of course this thing, as we mentioned before, is equal plus or minus gamma dot beta prime. So that because of this, okay, so that's where we got it from, and that's the end of this proof. So yeah, like I said, please do this yourself. It go much faster. and anyway, so we got to the end of that. So that's how theorem 5 is proved. And then let's calculate example B, the torsion. And we already, but now this time instead of calculating from the limit, which is a real pain, and we now can calculate it directly from the formula. Now to calculate from the formula, then of course we need the triple prime this time, which is why I wrote it. Or wrote it back in here when we were doing that. Where is it? Yeah. So going back to the example, I wrote down the triple prime values here. Okay. And then yeah, because the last one item is 0, so I only had to write down 2 of them. So once we do that, then write down the determinant of all 3 of them, which end up being that there were 2 zeros or something, so the determinant is not as hard as it normally is, an easy sample. So you calculate the determinant and divide it by this dot product is just 1/4. We calculated that earlier, so that answer came out 1 over t equals 1/2, just like before, but in a somewhat easier way. Of course, before we also already calculated x prime and x double prime, so that's one reason why this is so much shorter. Either way, so that example B then shows that everything works, and that's the end of. We have come to the end of this part. And let's talk about homework, okay? Right, okay. So for homework on page 100, please do problems 1, 2, 5, 6, 7, 9, 10, 11, 12, 13, 14, 15, and 16. Okay, so that should be it. So please go do your homework, and when you're done, let's talk about them. So now that you're done with the homework, let's look at them. First, problem 1, which is a direct computation. Let's see, okay? I have it right here, but I don't think it's much worth mentioning. It's just a matter of, taking the derivatives, calculating the tangent, calculating the cosine delta theta, applying that same trick that we did in the proof of the theorems, and then yeah, that's the exact same thing, and then something will come out, and then you come out with the right answer, and that's the problem 1. That's calculating 1 over r, which is the curvature, okay? And then problem 2 is the same problem, except that now we're calculating the torsion, so we do the same thing. And I think I even rewrote some of the stuff here. I don't know. Anyway, so let's, but this time we are calculating as s of 0 at pi over 2. But in this problem particularly, it is of no consequence, okay? That is where it is. That's because both the curvature and the torsion are constant for some helix, okay? A nice, smooth, round, no weirdness helix. So that's, so the S0 equal to pi over 2 doesn't come up. But in any case, so we'll keep it as S0, and then we calculate but this time we're gonna, being that we're doing the torsion, we calculate the gamma. Okay, and then what is that? Yeah, that's the gamma, which after some cranking, we calculate that, and then we need to figure out this thing, which is, well, whatever it is. And so e cos of pi equals to 1/2, and then we calculate the angle, okay, and that is cosine phi, which is that dot, as given by the definition, and which equals to the power stuff, and we pull the same trick as the previous problem, that delta s go to 0, and then 1 over t then equal to positive 1/2, because we need to write positive because the coefficient for x3 is positive, okay, and that means it's a right-handed helix, at least, yeah. Anyway, that's what it says on page what, 72 if you want to look at the details, something about right-handed. Anyway, let's see, then eventually we got 1 over t is some kind of a constant. And then, of course, this value right here is, what is that? Well, we calculate this thing, and then calculating t over here to be able to get, well, anyway, yeah, after some calculations, you can come up with the right answer. So next, let's, that is all the cranking, all right? Then next, let's look at problem 5, which I find somewhat challenging. So problem 5, I ended up looking for coming up with 2 solutions. The first one, I got out of Calculus 3 because Calculus 3 developed the curvature and proved it in, I find, a similar manner. So that's what I have here. Okay, so I imitated the Calculus 3 on page 289, but what we do is that, well, first, to make things clear, we'll call x of s the s parameterization as x, whereas r of t, we'll call it the x parameterization with t. Okay, so we'll call it r of t to avoid confusion. So r of t is x of s of t. Right? You just plug s of t in there, so it turns into a t formula. And so we'll call it r of t to not mix up with the x. But r of t is related to x, it's just the t parameterization. And then let's see, so then we'll calculate, of course, ds by dt as defined as x prime of t, which will, in this case, we'll call it r prime of t. So then r of t equals, we'll take the derivative now. R prime of t is then becomes x prime of t times ds by dt. In the previous problem, problem 12, I forgot to do the chain rule, this part, okay, which is why there's a mistake in the explanation, and I'm going to make a video to correct it. Okay. So anyway, so then that is, I'll mention that a little bit in a little bit as well. So anyway, our prime of t applying the chain rule is equal to that thing, or maybe it wasn't here that I messed up. I don't know, I messed up somewhere in problem 12 in the previous section, okay? And yeah, and anyway, so yeah, I don't think that's the mess up. This is where I messed up, okay? So our double prime of t is equal to, we'll take the derivative of the first term, okay, which earns another ds by dt, which that's the part I forgot, okay, in problem 12 of the previous problem. And so we have this, and so there's 2 of them. And then the product rule on the other side, of course, is take the derivative of the second term, so it ends up being that. Okay, so far so good, but what about it? And here's the trick, okay, that the Calculus 3 book did, is that we'll take r prime cross out our double prime. Why? No reason. We're just going to do that. It's kind of, like I said, it's kind of like proving trick identities. Sometimes we just do stuff with no reason, other than it somehow lead us to the right answer. So we're going to do the cross product for no reason. And then that will end up with that thing, okay, crossing this thing, right? So I wrote it out there, and then split them into 2, I guess. Yeah, because there's a plus situation here. So once you split them into 2, you notice that the second term, you end up with x prime cross x prime. Okay, anything cross itself is 0. So then when the one part just got, knocked out, which make life much, much better. So we still have this. Let's now take the magnitude of both sides. So slap the vertical bars around. And remembering that ds by dt is r prime, the magnitude of r prime, as we mentioned right here. Okay, because r prime is x prime of t. Okay, so then being that there's something is perpendicular, right, x prime cross x prime and x double prime is perpendicular, being that x prime is related to alpha, whereas x double prime is related to beta. And those 2 vectors are perpendicular, so is this. And as a result, the magnitude of the cross product is just equal to those 2 magnitudes multiplied by them together, okay? And one of them, x prime, happen to be equal to 1 because x prime is x prime of s, and x prime of s equal to 1. And previous, I don't know, page 95 or something. And so this whole thing then equals to x double prime, and as a result, then we what are we doing? Yeah, so substituting back in here, this magnitude end up being just x double prime, then we get, so x double prime is on this side, we put ds by dt on the other side as our prime, and that is the formula, okay? And that is what we are shooting for, and that's the first method, which seems quite neat. All right, the second method is from problem 12 of page 96. Let me find it. Now, as I've shown you in a previous video, which I haven't made yet, I hope I don't forget to make it, is that the problem 12 that I showed in the video before is slightly wrong, okay? Because I forgot to do the chain rule right here, okay? There should be a square here. And so as a result, then everything looks okay except the bottom part. This should be the fourth power. That is x double prime, end up having a fourth power. That's the only difference. Now, in that problem, I ended up getting the right answer because the magnitude didn't matter at the time. You know, I just skipped over the magnitude, which is why it didn't show when I was doing problem 12. But of course, now I decided to pull out problem 12 again, and now it is showing. So see, the second method, when I try to pull up from problem 12, where we already calculate x double prime of s, when I had 3 here, then the whole thing didn't work out, which is how I realized that I screwed up on problem 12 in the previous section. So anyway, then eventually I figured out that I forgot to apply the chain rule, and then then we're okay. So this is now power 4 instead of 3, and then everything worked out nicely because this magnitude, as we have shown earlier, okay, is just equal to those two things multiplied together because they're perpendicular, okay? Being that this is a cross product, and cross product is perpendicular to its previous thing that is being crossed. And as a result, then you can divide out one of these, and then so x double prime is equal to this exact formula that we were looking for earlier. So this is a much shorter solution, but only because we did most of the work in the problem 12 of the previous problem. But anyway, I thought the calculus 3 trick is worth mentioning. You say, why do we need 2 methods to do one problem? You don't have to, okay? But it's a neat trick that sometimes if you take the cross product for no reason at all, you know, something falls out. And especially when something goes to 0 or turns into 0, that make life a little easier. Because you might remember that calculating x double prime of s is not that pleasant, right? And so this is so that basically what this process did is avoided calculating what it really is. Okay, that is, we're only stuck with doing manipulating the magnitude without knowing what it really is. And so as a result, this is I think a neat trick that I happened to discover in Calculus 3. I covered Calculus 3 just a few months ago, but I've since, you know, this proof totally skipped my mind. But so I happened to notice it, and it works out very nicely. So I'm very pleased with it. So next, let's look at problem 6, where we are supposed to demonstrate the formula for the torsion, I believe, yeah, in terms of t instead of s. The formula, the theorem 5 we did gave the formula in terms of s, which is easier to derive but more difficult to use, because what if your curve is defined in terms of t, which is far more likely. So to rewrite theorem 5's formula in terms of t, we need to pull out some work. So here's what I did. Okay, gamma. So first, when I write gamma t as in the representation of gamma in terms of t, that is where x is parameterized with t. So I write it as before. I write the x of t as r of t to avoid confusion. Okay, but otherwise everything's the same. And as a result, ds by dt, which is x prime of t, will now be called r prime of t. So giving that r of t relationship, let's take the derivative as before. And so the derivative will be here, and there's the second derivative after we apply the chain rule correctly, okay, which means don't forget that the ds by dt here like I did. And then our that's our double prime. And this time we're going to do our triple prime. And the reason is because the formula we're going for has x triple prime in it. So I took the triple prime, which gave us something like that, okay? Let's see, no, it sums up, there are 4 terms, but it ends up being 3 of them. 3 terms, but still fairly long. And so yeah, okay, and then I wrote down gamma s is this is the representation for gamma s, and then I have the magnitude up here because we only in this problem we only care about the direction, okay, because we're doing well, we're doing some kind of dot product, so the magnitude is not of significant importance. Okay, so by now, so I wrote down everything. I calculated the the third derivative of r of t. Which is fine. So the question is now what? Okay, and now I'm stuck. So I didn't know what to do. So I beat around the bush, and then eventually I decided to take the dot product of gamma in gamma s dot out double triple prime of t. The reason is because if you do that, you notice that gamma has x prime and x double prime in there, and then and the final formula we have to get to x triple prime. So you know the cross product and then dot product becomes the determinant. Okay, so that's one reason for me to try this. Okay, that doesn't mean that this is gonna get us anywhere. It's just that like the previous problem when we did the cross product for no reason. And so now we're going to do the dot product for very little reason except hoping for that something good will come out of it. All right, so that's what I did. So I took the dot product and then and remembering that the gamma this is the relationship for gamma s, okay? Well, anyway, so to do the dot product, then I have right, what is that? So I only did, okay, so with the magnitude of gamma over here, so because I don't want to write it all the time, okay, and because being that we only care about the direction. So then, so we to do the dot product, then we get this thing, all right, and we're dotting the triple prime, so we have, let's see, okay, so we have 3 terms. Okay, out of the 3 terms, you notice that the first one, which is x, end up being x prime, x double prime, x prime in determinant, is 0 because it is a repeated row situation. Similar to the second one, okay, it's also 0, again because of repeated row. So we only have the third one left. That is a great sign, okay? It's always great when all these complicated things go to 0 and we only have one thing left. Okay, so then, so this thing equal to the last item, which is which is let's see, x prime, x double prime, x triple prime times ds by dt. That is an excellent sign because it's looking more or less like the answer we're seeking for. All right, and then so let's see, what's this? So then I divided by the double prime, and so we got here. All right, so we're looking pretty clean. And then we'll replace gamma s with gamma t. All right. Why didn't I just start? Well, I don't know. Anyway, that's what I did. Okay. And so gamma t, if we plug it in, gamma t is slightly more complicated than gamma s. Okay. On page 96, here's the formula for gamma t. Remember R of t is x of t, okay? I just want to not confuse it with x of s, so I write it this way. So we take the dot product, that equals to, let's see, okay, that's still equal to the other side, okay, which is that thing. And remember, ds by dt is x prime of t, which is r prime of t, by the way. And so, yeah, bearing that in mind, and then we write things around a little bit. So I divided the x prime of t or something on this side, so we only have r prime of t got down here. Okay, so now we only have x double prime of s in the denominator here. There is a squared here. Did I miss something? Let me check. Oh, the reason there's a square here is because I stuck it on purpose, okay? Because we're trying to fit into the formula that we're looking for. Because the torsion formula has x, yeah, let me look at the torsion formula again. Yeah, the torsion formula, yeah, the torsion formula has x prime, x double prime dot x double primes, that is the magnitude squared, and we got to make it to come out. Anyway, so that's why there's a squared here. So I multiplied another one down here and then put another one on this side, okay, of the equation, and move the x prime over here as our prime. So here the equation looks like that. And remembering that what is x double prime s? X double prime s equal to this thing. And this is from number 5, okay, the previous problem we did, okay. All right, so then if we put it another way, x double prime equals to this, okay, dot equal to this thing. And then, so then if we stick another one down here, then the whole formula comes out to be, let's see, equal to, yeah, so then this thing comes out to be exactly that, I guess. Let me check to make sure I can't read it from the computer screen very easily. Yeah, it does check out, okay? So once you plug this thing in, so because x double prime t, plug it into this side, then you have a x t squared situation. That is x prime of t cross x double prime of t and magnitude squared. And where, of course, our t equal to x of t, remember that? So then this formula that we're looking for does end up being the original formula in Theorem 5 that was given for the torsion. Okay, so that is we have finally come out with the answer. Now that looks a bit messy, but if you look at it carefully, it will all make sense. The trick in problem 6, of course, is taking this dot product. Okay, without the dot product, then we're gonna be not so happy. And well, there's probably a way to do it brute force, to just simply crank everything out and see that it equals, but who wants to do that? That's like way too hard. I mean, way too tedious and annoying. So this is much better, okay? So the dot product, which created 2 zeros, is will give us the neat trick and shortcut to get to the end of problem 6. So that is quite nice. Of course, it also depends on problem 5 as well, where we calculate, we already know what the magnitude of x double prime is. So that helped as a result. So problem 6 is more difficult than the rest of the section. So now that we have got through problem 6, then problem 7 is a lot simpler. And now we can relax a little bit, okay? Proving that the plane curve has torsion equal to 0. That is fairly straightforward from the definition of plane curve. Then you calculate the torsion, and very soon you realize the determinant of the torsion has some kind of a multiple of one row of the other row, and therefore it is 0. And then the next problem, problem 9, that's just a direct calculation of the twisted cubic, which is fine. Let's calculate all the derivatives and follow the formula. What is the formula? We're calculating something. What is that? 1 over r, okay? And then problem 10, where we calculate 1 over t. So 1 over t, shouldn't it be a triple? Yeah, there's an x. The third derivative, which is why I wrote it here, because in problem 9, we only need a double second derivative, but I saw problem 10 coming, so I might as well wrote down the third derivative too, and then everything comes out okay. So that is the answer for 9 and 10, which are relaxing after we grind through problem 6. All right, so next let's look at problem 11. So that is a simple matter. We're dealing with lines here. Okay, what are we doing? Something about the, curvature. A straight line has no curvature. Yeah, that is a quick application, plugging into the formula. It doesn't matter which formula. Well, the line's parameterization is with t. So then we'll use the formula for curvature for with t, which is number 5, okay, problem 5, and plug it in, and everything comes out nicely. Problem 12, we're going to prove that the plane curve implies that torsion is 0, and the other way around too. Problem 7, we already did that. The plane curve implies the torsion is 0. Now, if the torsion is 0 on the other hand, then of course the triple x prime x double prime x triple prime determinant will be 0, which means that this is a plane curve, and that's proved back in theorem 3 on page 73. And I'm not going to go too much into that. And so next, problem 13, we're supposed to calculate beta prime, right? Yeah, so we'll get the definition of beta prime and crank it out. Okay, it equals to that, and so on. Well, this one we already did, but I redid it here. Is the same thing. Okay, so that is, yeah, which equals to this, and then that's beta prime 13. Continuing, we have to calculate, oh yeah, beta prime, we have to not just calculate the derivative of this, which is just the numerator. Okay, we need to calculate the whole thing, which is, but we need the numerator, so we know what to plug it in. So doing this, the derivative of the beta in S, then we calculate a bunch of stuff and apply the quotient rule. Okay, that becomes, and then we get a bunch of stuff, and then we'll do the product rule and sort this out following the product rule definition on page 64. And then eventually we'll end up with the beta like they want it. All right. And then next, let's look at problem 14, which we're going to do calculating gamma prime. Okay, because gamma prime, remember gamma prime is in the proof of theorem 5 is how we came up. Gamma prime dot gamma prime is equal to 1 over t squared. That's mentioned in theorem 5, the proof of theorem 5. So that's what we're going to do. We're going to calculate what is gamma prime in terms of alpha cross beta, being that we already did beta prime. Okay, so then gamma prime then equals, we'll calculate it directly, and we're taking the derivative. What is this? It's S. Okay, we're doing S. So and okay, then gamma is alpha cross beta. We'll calculate, was it S or T? What is that? Is that yeah, I'm pretty sure it's S. Anyway, so we calculate gamma prime, which end up alpha prime cross beta end up being 0, and then so because they're the same vector, right? And so that gamma prime is just alpha cross beta prime, and then we use the previous solution as answer, which is right here, and then do the cross product. And then this we use, what is that? It's the triple cross product again, okay? And make things come out, and something here, right here, alpha dot beta equal to 0. So this part is 0, and we got gamma prime equal to this whole deal, including the negative sign, which is what the answer says, right? That becomes the, what is that? That is the determinant, okay? Which I didn't write it out because but that is the what the answer wants. Yeah, it ended up being the determinant over, well, x to the power cubed. So that's problem 14. And finally, problem 15, now that we know what gamma is, we calculate gamma dot gamma, which is 1 over t squared, as seen in the proof of theorem 5. And well, we calculate, once that's calculated, we end up being that thing, okay? Then take the square root, then 1 over t equals to this. And of course, there's a plus or minus sign that I didn't bother, but you get the idea. Then finally, problem 16, we have to, we're going to calculate the everything directly. That is, we're going to calculate gamma prime by simply taking the derivative of gamma, and this is with respect to S. All right, so let's do that. So that's what I did. Okay, let's calculate the derivative of gamma directly, which then gamma prime equals to that, and we have, so after a bunch of remembering what the magnitude of well, whatever. The point is, let's do this thing, And well, we already did this several times, but I did it again here. And so gamma prime, then after applying the quotient rule, right, we got to this point, which is this, and that was all very fine, but then I was confused as to what to do. Now what? This thing doesn't look like the Lagrange identity. It doesn't look like anything that we've seen. So I was puzzled at first, but eventually I realized that what we need to do is let's factor the x prime out of the cross product, because it's crossing here, okay, and then crossing over here, the same x prime. And normally, so far we've only expanded any cross product. We've never factored it out before, but there's nothing wrong with factoring stuff out. So once I factored it out as x prime, the common factor out of the cross product, then we got here. Now this is exactly this is exactly what happened in problem 13. So we got to problem 13 at this point, okay? So then we can reapply problem 13 and 14 and got to the answer right away. We don't have to redo those because we already did it, and that's the answer. And how we got, so we are able to calculate the formula directly as well, okay, instead of pulling tricks, which is what the book means, is that we can prove theorem 5 without any sleight of hand. That is, no tricks. But I like the tricks better, okay? To take the derivative directly is not as exciting, although it did remind me that sometimes you can factor this thing, okay? There's nothing wrong with factoring if when you have two common factors, right? So and so I did learn that out of this, reminded me of the factoring business, and so that makes the end of, that is the end of this section.